There's a reason why the first 50, 60 years of Flywheels was for this uninterrupted power supply application. We are trying to optimize for all of that and build a product that is ultimately competitive with the other forms of energy storage that are in the market.
This is EnergyCast, and I'm Jay Dowenhauer. Today we're talking about flywheel technology, using kinetic energy from a centuries-old invention to store electricity. I've done several energy storage episodes in the past, and as we've learned, they don't all have to be chemical batteries. Remember that episode where energy was stored in ice? Conventional electric utilities have not always considered energy storage as important as they do now. For decades, electricity was produced as it was needed. Families came home and turned on their appliances, and other power plants spun up to answer. But as we've discussed, if you can defer or store power for when you need it most, fewer power plants can run more consistently. You're leveling out the demand for power. And as more renewable energy comes online, their enormous benefits come with the catch that they're not going to run all the time. Energy storage can fill in these gaps even for a minute, for instance, when a cloud passes over a solar farm. We're going to see a growing cottage industry of energy storage solutions out there, not all batteries. In the same way we don't want to see an energy portfolio that's one fuel source, we probably don't want to see an energy storage sector that's all chemical batteries. That brings us to flywheels. They're nothing new. Neolithic cultures were using potter's wheels 10,000 years ago. Machines started incorporating them at the turn of the millennium, the last millennium, and of course they were critical to the Industrial Revolution. Last spring, my wife Ashley and I visited the Discovery Place Science Museum here in Charlotte, and one of the exhibits showed off some of Leonardo da Vinci's inventions. Sure enough, Da Vinci had his take on the flywheel, and there's a picture of me playing with it up on the website. So, what's a flywheel, and what does it do that's so important? Basically, it functions like a gyroscope. A big heavy wheel starts spinning, and the inertia stores rotational energy. You spin these things up fast enough, and they'll store a lot of energy until it's time to use them. Now, we're friends, so I'm going to admit something that's a little embarrassing. I've covered a lot of technologies, and had the hardest time getting my head around this technology. Maybe it's because it's so simple and I thought there was more to it, but as I was cutting the interview this week, I realized I did not fully grasp how our guest's technology worked. Now, I asked some friends and coworkers for help and even considered reaching out to my high school physics teacher. I had flashbacks to those magic eye pictures from the early 90s that had those hidden pictures in the mosaic.
If you stare at these things long enough, you're supposed to see some kind of hidden three-dimensional picture.
Oh, yeah, look, it's a sailboat.
You saw it too?
What?
I've been staring at this thing for a week now, from opening till closing, and I can't see a thing!
You gotta relax your eyes.
Everyone sees this thing except me.
Yeah, I never could see those either. Finally, I called one of the company's employees, and we spent another 49 minutes going over the technology so I'd have it right for this monologue. So here it goes. The flywheel consists of a large steel disc attached to bearings that power both a motor and a generator. The system is designed to deliver 8 kilowatt hours for 4 hours, so 32 kilowatts. The motor, also 8 kilowatts, speeds up the flywheel to 9,000 RPM. Ideally, the company would love to see this motor powered by renewable energy. Wouldn't we all? As you'd guess, this flywheel would start slowing down once power was no longer applied. To combat the friction, the flywheel has been placed in a vacuum-sealed containment, and magnets lift all but 5% of the weight of the flywheel off its bearings. Then a small draw of power, averaging just 100 watts, about a light bulb, keeps the flywheel spinning, kind of like giving a small push to a spinning plate. Now, when it's time for this flywheel device to create energy, it engages a generator, producing, again, 8 kilowatt hours of electricity for 4 hours. During these 4 hours, the flywheel gradually slows from 9,000 RPM to 3,000 RPM, and that's a low limit that they call the zero state of charge. What's cool is that though the speed is gradually dropping, there's no gradual drop in the power being created. That's steady DC current. The DC current is converted to AC, and the energy that was stored in this flywheel is released into the grid. Thank you. Thank you very much. Whew, I feel like I deserve a PhD for that, but for a real PhD, we can talk to our guest. Dr. Bill Golub is the Vice President of Business Development for Amber Kinetics, the flywheel company I've been describing based in the San Francisco Bay Area. Bill spent much of his career developing wind energy projects, including wind energy for Chevron. He joined Amber last year in 2017. I hope you enjoy my conversation with Bill Golub.
We're here with Bill Golub, Vice President of Business Development for Amber Kinetics. And Bill, mechanical flywheels, they can trace their history back to medieval times, and of course they have evolved in the years since. So help us understand what is happening in a flywheel as it's building up energy.
Sure. I'm going to take you back to your most basic physics, which says that any form of energy can be converted into any other form of energy. Effectively, what's happening is that when the flywheel is spinning, it is storing kinetic energy or energy of motion. And through the power electronics and the equipment within the flywheel unit itself, it's converting that kinetic energy into electrical energy.
And so a flywheel for this purpose is a battery, right? And,
absolutely.
And what sets it apart from a conventional chemical battery? No chemicals, right?
That's it. Chemical energy is the energy that's stored in the bonds of the molecules. Kinetic energy is the energy of motion.
The benefit, of course, here is that you are getting a delay in energy. I just want to make sure I've got this straight. According to your website, you say one module can release about 32 kilowatt hours over 4 hours.
That's correct.
Okay. How do we need to think about the energy that's going into getting the flywheel going?
You would think if it was a perfect system, which physically it cannot be by second law of thermodynamics, it would take 4 hours to charge and 4 hours to discharge. But because it is a system in the real world, it actually ends up taking about 4 hours and 40 minutes to charge fully and then 4 hours to discharge fully.
And I'm also thinking, Bill, about the flywheel a lot like spinning plates. A bit of energy to get them going, and then every now and then a little bit of energy to keep them up to speed, but not nearly as much. Do you give it a little jolt of energy to keep the rate up, or do you have it going and then it's 4 hours? How do we need to think about how the energy's working?
What stops a plate from continuing to spin once you start it? It's some kind of friction. In the case of a spinning plate, it's actually very similar to the case of a flywheel. In our case, it's the contact with two bearings, an upper bearing and a lower bearing, which hold the flywheel rotor in place. And the other source is rubbing against those bearings. And then there is a very small amount of friction between the flywheel and the atmosphere, just like with the plate. Because of the way electricity works, it's really a continuous supply of power. We are constantly giving a very small amount of juice to that rotor to keep it spinning at whatever speed we want to maintain, whether that's 9,000 RPMs, which means it's fully charged, or some lesser quantity of energy for some reason.
We're not just spinning it up during off-peak hours, and then during peak hours, it just spins till it stops, right? You're continually feeding it a small amount of electricity to keep it going. It's continually going, right?
Yeah, so you can think of, in a sense, two states. An active state where it's either charging or discharging, or a resting state where it's spinning without performing any work. It's not charging, it's not discharging. So when you're just keeping the flywheel at some state of charge, it takes about a light bulb worth of electricity to maintain that state of charge. Let's say, for example, you charge it up fully and you're rotating at 9,000 RPMs. You need about 100 watts to keep it at 9,000 RPMs and overcome the two sources of friction that I described to you. If it's spinning slower, it's at the 3,000 RPM, which is what we call our zero state of charge, meaning we won't let the flywheel convert any kinetic energy into electric energy. At that rotational velocity, it takes about 40 watts to keep it spinning. So when you're not charging or discharging, you're putting an old style light bulb worth of energy into it to maintain its rotational velocity.
Okay. I came from oil field. I'm a big fan of tough hardware that doesn't break easily, and these modules look like they're made of solid steel, essentially. How much maintenance do they require? How tough are these things?
Oh, they're very tough. As part of our safety program, we've tried to get these things to self-destruct and tried to figure out what that takes. And we have to cut them up pretty good before they'll consider breaking up. They are, as you suggest, they're made out of aircraft steel. It's an alloy that's used in the aircraft industry. And the product is about 98% steel. So the toughness and the strength is there. The maintenance that they require, interestingly, is very little. One of our commercial claims is that the only maintenance you need to do is at 10-year intervals, where you need to replace the bearings and the power electronics, which are not steel products. That's it. 10 years and 20 years, you really shouldn't have to do much at all in the way of maintenance.
10 years, and the idea is that they have been pretty much rotating the entire time?
The way that we think about how these might degrade is in terms of cycles. The stress on the rotor from staying at a given speed is extremely small. That rotor would last a very, very long time, 100 years, if it was at a constant speed. What puts the stress on it is going through different rotational speeds. We think that if you were to cycle more or less continuously, about 2.5 cycles a day, 4 hours to discharge and 8 hours and 40 minutes to charge, you can get a little under 3 cycles in a day. The product is designed to last 20 years with that kind of cycling.
That's pretty impressive. And in researching this technology, I came across a NASA-sponsored flywheel design that apparently has a rotor held in place with magnets surrounding it, so it essentially floats. And I believe that your design, as it was described, also had this magnetic component as well. So tell us how your designs compare to those and maybe even other commercial flywheel designs that are out there.
There are some very, very fancy magnetic bearings that make the friction extremely low. But if you do a cost comparison between that and a conventional magnetic bearing, there is a little bit of friction. But if you look at the cost benefit, going with the maglev approach, which is, I think, probably what you were looking at, is much more costly. And so it's really not, at least at this time, we don't think that commercially that's the right approach to take.
And one more thing, mechanically, what's going on with these things? The vacuum design and the magnets that help nearly eliminate the friction on the bearings. You're also engaging a generator when you're making power. Help people understand, is that creating any friction on the flywheel? What's happening there? Because you're at times engaging a generator, and that's, of course, slowing things down a little bit. Right?
Yeah, that's why it's not a perfect conversion. And there's a measurement called the round trip efficiency, which measures the losses that you incur between the amount of energy that you take in when you're charging your system and the amount of energy that you discharge when you're discharging your system. I think our most current spec sheets were about an 86% round trip efficiency, which is quite good if you compare that to other technologies.
Sure. In your website, you describe low and medium flywheels, which can do up to 10,000 RPM. I believe you said that yours do up to 9,000.
Yes.
And then there are what you call fiber composite units that can spin up to 100,000 RPMs, a whole nother order of magnitude. So any plans to move into fiber composite, and what are the drawbacks to going to a design like that?
Well, it's not so much drawbacks, it's that the application is generally different. Historically, flywheels have been used for the purpose of creating an uninterrupted power supply type of device. People are probably familiar with the idea that our electricity is 60 hertz, and different types of equipment are sensitive to different variations away from that 60 hertz. The UPS keeps it right on or very close to 60 hertz. In the case of utility grids, where the frequency events are typically less than a second to a few seconds to maybe a couple of minutes at most, the fiber materials are really good for that very short duration, high power burst. But what they're not good for is providing energy. What we've discovered is that steel is a much better material on a per dollar value basis for creating a flywheel that is trying to serve an energy storage purpose as opposed to a UPS purpose. And so rather than say that there's drawbacks, the applications of the material are different.
Okay, well, good point. You've positioned this technology to operate in 3 sectors: behind the meter, microgrids, and utilities. So which one of those excites you the most?
That's a tough question because the distinctions are already starting to blur. We're working on some grid-embedded microgrid projects where the microgrid serves some set of customers. Those customers and the microgrid itself are behind the utility meter, but the scale is traditionally what we would have called a utility project. Mm-hmm. We are currently looking at projects in all 3 sectors. and are frankly really excited about all of them.
And tell us about some of the projects that you've done.
One of the key differentiators of our flywheel is that there is a limit to the number of cycles that a chemical battery can perform. The chemicals simply won't react in the same way anymore. And in fact, the reaction of those chemicals degrades over time. Your listeners will be quite familiar with what happens when you buy a new smartphone.
Yeah.
And by the time you've had it for 2 months, you're barely squeaking out 6 hours. That doesn't happen with a flywheel. As long as the mass of the rotor is unchanged, and there's virtually no way that it could be changed, the amount of energy that it can store does not degrade. Any application where there is more than one cycle a day is good for us. We have a utility demonstration project right now pairing a solar project in a high solar area, but it happens to be an area that gets a lot of transient clouds. The solar output drops and increases many times each day. We're using the flywheel to smooth out that solar production.
That example is wonderful. Let's talk about, we're doing several kilowatts per unit, but talk about getting to megawatt hours of deployment. Is there an answer to go bigger, or is there a theoretical limit to how many or how much power you want to create at a single location? What thresholds are you working in as far as that's concerned?
As far as I know, there are no theoretical limits. The limits are really on the engineering. The largest flywheel design that I'm aware that we've looked at is about 1 megawatt. So that would be a 4 megawatt hour unit. But that's going to be really, really massive. Once it's installed, it's like any other really big piece of industrial equipment. You don't want to move it.
Yeah, and if I'm doing the math correct, if you're doing 32 kilowatt hours now, to go to a megawatt would essentially be about, 120 times your current design, right?
The rate of energy discharge.
Right.
We will not be going to that size in the next couple of years. There's a number of things that we can do in the interim to make the product more cost effective.
All right, so we're going to finish with a lightning round of your thoughts on different energy technologies, and this can be short form answers, starting with natural gas.
I think it's got an application for some relatively short period of time, but people are going to be surprised at how quickly all fossil fuel is overtaken by renewable energy.
And then another fossil fuel, crude oil.
Yeah, crude oil is made from dinosaurs, and in the not too distant future, we will think of that as a dinosaur as well.
Okay, and then the other fossil fuel, coal.
From my point of view, is the worst form of energy because the global warming contribution from coal is just over the top.
Nuclear.
Nuclear is one of those sort of tantalizing technologies that if it could be done safely and if it could be done for the costs that people hope it could be done for, it could have great potential. But because we have never come close to realizing that, and because of, let's say, the national security risks associated with nuclear, I don't think you're going to see a lot of nuclear development going forward.
Wind.
A great technology. Of course, it has its downsides, but I think that wind will be one of the 2 or 3 primary sources of energy for the world in the next several decades.
Solar.
The word that comes to my mind is inevitable, so that you understand what we're actually talking about. Every day, the amount of solar energy that strikes the Earth could have powered all of human activity to date for all time. It's only a matter of time before this is really our principal source of energy, and it's happening much faster than really anybody thought.
Biofuels.
Biofuels, I think, are critical. The drawback of the 2 energy sources that you've mentioned so far, wind and solar, that I think have the most promise, is that you can't control them very well. Using renewable energy to generate biofuels and generating renewable biofuel provides a very, very good, very effective long-term source of energy storage.
Hydroelectric.
Hydroelectric is, one of those things where I think it's going to be around for a very long time. I'm hearing about some new forms of hydroelectric that can convert man-made sources of water into electricity in a way that doesn't necessarily have a lot of environmental impact. The days, certainly in the U.S., of building big dams and all that's entailed with that, those are almost certainly behind us. But facilities tend to last for a very, very long time. It probably makes a lot of sense to think about keeping those things going.
Geothermal.
A great source of energy. There's a couple of different ways it can be used. The problem is that the science of determining what the geothermal potential is very, very tough, and it's very expensive to validate a geothermal resource.
I didn't have you guys, but let's throw your technology in, flywheel technology.
I think that it's going to be an important part of the new energy mix. The reason that I changed the direction of my career and joined Amber Kinetics was that the technology solutions that we have right now for storing energy on the timescales that batteries and flywheels operate, there's a big role for flywheels.
Electric vehicles.
Absolutely the way of the future. The internal combustion engine has a very short life ahead of it.
Energy efficiency.
My favorite on your list.
And then finally, nuclear fusion.
Yeah, wake me up when they have something to say.
Isn't that always okay? All right, Bill Gull of Amber Kinetics, thank you so much for your time.
You bet. My pleasure.
That was Bill Gullove, Vice President of Business Development for Amber Kinetics, a flywheel energy company based out of the Bay Area. I looked at other flywheel companies out there, but one of the unique ways that Amber stages their flywheels is just below ground, in corrugated steel tubes arranged in a grid pattern like whack-a-moles. I asked about this and was told it was for safety. The flywheels would have nowhere to go, spinning at nearly 10,000 RPM. I also think it's smart because you don't have to build big enclosed buildings around these units. You can find pictures of that and more online at energy-cast.com and on Instagram at hostenergy. I want to thank Bill for his patience and Mark Stout with Amber Kinetics for taking nearly another hour to help me with my follow-up questions. Hopefully, I did you justice. All guests are sent the raw and completed audio the week of release. So far, no complaints. Music was produced by Sean Stroop at Stroop Loops. Be sure to rate us favorably on iTunes. That helps build the audience. That wraps up episode 43. Be sure to join us next time when we explore the wide-ranging implications of liquefied natural gas exports. You won't want to miss it. Until then, I'm Jay Downhauer. We'll see you next time.